All right, my name is Luke Natty, and I will be going through my lab 2, which is gravity and drag interacting on a falling object. So table of contents right here: introduction, data observation and models, code, discussion, then conclusion. So introduction: this lab is conducted with the purpose of seeing an object's motion that is dropped and slowly falls. The fundamental principle at work here is Newton's second law, otherwise known as the momentum principle. A computational model that only considers gravity and another that considers gravity and drag will also be compared. In preview of the results, gravity and drag both act as forces that influence the falling object's motion. So Newton's second law, known as the momentum principle, states that force is equal to the change in momentum over the change in time. It indicates change in movement within a system and the surroundings. This is very important to know for this experiment. Other important terms: gravity acts as a force of attraction which pulls an object towards the center of a body of mass. The result of Earth's acceleration due to gravity is 9.8 meters per second squared. Then drag is a resistance force that acts against the motion of an object falling through air or water, acts as an opposite direction of gravity. So procedure: first, an object falling was recorded and uploaded into the tracker software. In this case, I used a buzz pillow. Use the center of the mass calibration stick and axes to properly record the data frame by frame. Then you have to create two computational models, one showing only gravity's effect, one showing gravity and drag. Then these need to be compared to the tracker data in its relation to Newton's second law. So for the tracker data, there is the buzz falling right there in the middle. You can see that velocity increased over time and then started to become a little bit more linear towards the end, but overall velocity increased, position went down as it fell before it eventually hit the ground. So some observations to be made for the tracker data: start time was 0 seconds, end time was 0.767 seconds. Initial velocity was 0 in all directions, x, y, and z. Initial position was 0.0181 for the x, and then negative of that for the y. The system in this case was the buzz pillow, and the surroundings were anything else affecting it, which was the air, the gravity, what have it. These observations will be used to see the impact of gravity on the object's motion. So for my code, for the gravity model, I used the starter code, but then I changed the mass to the mass of my pillow, which was 340 grams or 0.34 kilograms. The position was the starting vector that I talked about earlier, the 0.0181. Starting velocity was 0 in all directions. The end time was 0.767 seconds. Net force was set equal to weight, and then weight force equation was also added, and then velocity update and position update formulas were added. So for the gravity models, you can see that the object was overall accelerating throughout the entirety of the time. It doesn't become linear. The object just continues to go faster and faster before it stops. But then for gravity and drag, you add in a B value, the drag force equation, the net force equation, and then area equations and scales to show the directions of the forces. And this gives you a gravity and drag model where you can see the velocity starts to linearize towards the end. And that's because it is getting closer and closer to reaching terminal velocity. And then these arrows on the side here show the force of gravity and the force of drag acting upon each other, and they eventually balance out to reach terminal velocity. So for the comparison, both models were very similar, but since gravity did not take into account drag, it was overall faster, and they continued accelerating while drag started to become more linear. Potential errors, mistakes could have been made using the tracker software. Additionally, in the video model, it would be impossible to not have drag interacting with a falling object, so Buzz would have been experiencing drag. So which model better predicts terminal velocity? Definitely the gravity and drag one, because you can see that it becomes linear towards the end. Now that is terminal velocity, where the velocity becomes more constant because the net force equals 0 and gravity and drag equal each other out. So what if the object was thrown? So if the object was thrown, it's not exempt from reaching terminal velocity. If it was thrown down, the object would initially accelerate faster because of that, but it would still reach terminal velocity where gravity and drag equaled each other out. It would just hit that linearization faster. So conclusion: the momentum principle, which is Newton's second law, is observed in the video model through the object's acceleration, mass, and force interaction. Force grows as mass grows, same with acceleration. Identifying which computational model better represents the experimental model. The gravity and drag model better examples what is going on in the experiment with Buzz, since the real object has to undergo drag force. And then gravity and drag computational model is near exactly like the experimental video model of Buzz being dropped. Data collection overall was very consistent, and they lined up pretty accurately. Thank you.